Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream, no engines, no libraries. We are attempting to show the complete development of a game here, right down to the very last little pixel. And we had finished up a bunch of major work we were doing on Wednesday, and so yesterday I decided we might as well just do something kind of fun and whimsical. So what I thought I'd do is I'd show how to make particle systems. So yesterday we made a particle system. And I guess I should say before I go any further, if you pre-order the game on handmadehero.org and you want to follow along at home with this episode, today is day 156. So you should go ahead and take day 155 source code, unzip it into a directory, and that's what I'm going to be starting with here, just so you've got kind of the same state as I have, the same codes as with a Z. And so what we did was, really, I just showed kind of the very basic idea of how to make a particle system, and you can see that because it's the sprite that we happen to have lying around, we use the head, and I think people sort of ended up kind of liking the head particle, and so it's kind of stuck there. I was going to say let's make a little sphere particle to put in there, but people seem to like the head, so I don't know. Maybe the head has to stay in there. But point being, you have this little particle system here. And so what I wanted to do today was just finish up kind of talking about particle systems and some things, maybe showing a few more things that you might want to do with them, and just kind of, again, this is kind of a 2-day sort of intro to particle systems, and then we'll wrap it up, and Monday we'll start on doing our asset system memory management stuff. So, okay, so, hopefully everyone understood roughly what was going on there. Particle system is a pretty basic idea, right? Ooh, that's no good. A particle system is basically just a lot of little low-cost entities to simulate, right? The idea behind a particle system is you're going to throw a lot of sort of cheap things at the problem instead of having like an entity, a whole entity, which in a game can be very complex and have a lot of simulation logic and can take on a lot of different roles. We're going to make a lot of small, cheap, uniform, fast, stuff and throw them at the problem to sort of do this simulation for things that entities don't simulate particularly well, like mists and liquids and gases and that sort of stuff, like we talked about. And so that's what we wrote. And there's some things that I thought I wanted to sort of show you to extend sort of what we did yesterday, just again as sort of getting your feet with particle systems for people who haven't really ever done any particle system programming before, which may be some of the folks out there. So what I wanted to say is, I wanted to take our particle here and do a couple more things with it, and a couple more of the traditional things that you might do with it. And so some of them are, the first thing I want to do is say, let's add an actual acceleration to the particle, right? So that when the particles are spawned, we will have a little bit more information about what they're going to do physically, right? And so in order to do that, you can see that as we spawn these things, right, I could then say, well, you know what, let's make particles subject to gravity. So, they're going to fall down, they're going to fall down at some rate. And that rate, let's say, is going to be, negative 9.8 meters per second squared, right? So our acceleration is going to be the standard acceleration of gravity. And then what I want to do is I want to come in here and say that the particles, when we update the position like we did here, we are also going to update that velocity, right, by adding it in. Now, what we can do when we do the update the velocity, we can just do the sort of standard two-step thing where we update the velocity and then update the position, which is not quite accurate, right? If we were worried about saving every extra little tiny cycle, maybe we would do something like that. But we really don't have to do that. Instead, what we can do is the full equations of motion, like we talked about, 1/2 at squared. I assume you guys remember this from when we talked about it, to account for the complete effect over the entire time step of that, of that acceleration, right? So I'm just going to go ahead and type that out. And if you don't know what I'm talking about, then it would be a good time to go back and watch the episode on equations of motion, so that you know why I'm adding 0.5f times the time step squared times the acceleration into the position. And so that's a little bit more of an accurate integration, but again, it would work regardless of which one you were doing. And again, since particles are supposed to be sort of fast, cheap hacks in a lot of ways, really any way that you want to update it that accounts for acceleration in some reasonable physical fashion is probably going to be fine, right? So let's take a look at what happens if I run that. Now, you can kind of see those guys falling down, right? Kind of like a sort of a waterfall effect sort of thing. And so in order to counteract the effects of gravity, we probably want to start them with a stronger upward force, right? So, you know, if we were going to, and I'll use, again, I'll lean on the live code editing system that we did here to help us understand what's going on. You know, when we create that sort of dp, that sort of velocity vector, what we can do now is just kind of beef up our upward motion, right? So instead of just between 0.7 and 1, I can really just kind of jack that up by adding a little multiplier on the front that just gives them more of an upward thing. And now you can kind of see how we've got more of a fountain effect going, right? And I want to talk a little bit more about the fountain effect because I feel like it's important maybe at this point, just when we're talking about it loosely. And again, since these are kind of fun days, I want to kind of bring in, you know, we're just kind of playing around with the particles and getting you interested in them. I want to bring up a couple things about particle systems that you may not know, even if you've done particle systems before, or that you may not be familiar with if you're not like a physics sim guy or whatever, right? So I'm going to point out some things there. But before I go into that, I'll just take our little fountain here and say, you know, one of the things that's not very good about our fountain is when these things hit the floor, right? When these things, you know, collide with the floor, they should probably bounce, right? And as you know, collision detection is pretty difficult. You know, we spent some time on it. We still have more stuff we have to do. Our collision detection is kind of rudimentary and not really great. And so we have some things I said when we want to go do our final pass on that. We have some more things to do. So, you know, can we really afford to do any kinds of fancy collision detection on our particles? And the answer is maybe not so much. But just because we can't do real good collision detection on our particles, remember, particles are about doing something fast and cheap that allows us to create some interesting phenomena. And we can do some things that would allow that to happen. So, for example, one thing that would be pretty trivial for us to do is just to check to see if we cross below sort of a ground line. And if we do, just bounce ourselves back up, right? And so it would be pretty easy to do something like, you know, if particle P, or even, you know, I could even do it in closed form. I could just say, whatever the particles, I guess it was y is our thing here, absolute value, particle P dot y. So I could say just don't let the y value go negative, right? And you can kind of see how it now does this sort of, it kind of has a nasty vibrating effect for a reason which I'll talk about in a second. But you can kind of see how we can start to put in a fairly cheap effect, right? That will make it so that our particles will kind of land on something. Now, we really don't want them to have that kind of nasty bouncing effect. So there's a couple different ways we can do that. What that bouncing effect is coming from, if I may go to the whiteboard, or blackboard, I should say, for a moment, just to kind of draw it out so you kind of have an idea of what is going on there. So what happens when I have this bounce situation is the particle is coming down, right? And you have to remember, everything is happening nothing really happens on a curve in our graphic stuff. Everything always happens in discrete steps, right? So it's like here, and then it moves to here on the next frame, and then it moves to here on the next frame, and then it moves to like here on the next frame or whatever, right? And if the ground is here, if I'm going to negate its position, so I'm going to take this mount and flip it back up, right? You know, that's going to like oscillate this guy very quickly because he's going to come here and then gravity's going to pull him back down again, and then he's going to come here and gravity's going to pull him back down again, and so on, right? So what I'd rather do is something a little bit more like what we were doing before, where I say, okay, if he goes below it, let's just set him, maybe project him back to the point of contact, and maybe just negate his velocity. So instead, he'll bounce and kind of go up, right? Because remember, we did that when we sort of did our stuff there. So what I'm going to do instead is say, if the particle py, right, is less than 0, then I'm going to make the particle py equal to 0, and I'm going to make the particle dpy equal it's negative. So I'm just going to flip the direction. I'm going to bounce it off that surface, right? And there you can see now I get kind of a more natural bounce, right? And of course, the other thing I can do is if I wanted to, now that I've taken care of that velocity problem and it won't go back in immediately, I could choose to try and keep some of that momentum there by doing something like that as well, right? So now I can keep that negation. That was like the absolute value thing we were doing before, right? So now we've got those bouncing heads, but you'll notice what happens is they bounce as high as they fell, right? And that's actually the physically correct thing to happen. If you let something go and it bounces off the floor, its natural physical thing to do would be to bounce as high as you dropped it, right? That's actually what should happen if you were just looking at the strict equations of motion for the bounce. But the reality is there's a couple different things. There's drag through the air, right? So there's energy being lost there. And so that will account for a little bit. But what really accounts for the majority of why something doesn't bounce as high as when you originally at the height when you dropped it is actually the impact with the thing that it's hitting. So if I drop a ball on the floor, the reason it doesn't bounce as high as from where I dropped it is actually because there's energy that goes into deforming the ball and to some very small extent usually the floor slightly. Those atoms, as they intersect each other, as they kind of squish together, there's energy that's lost in that actual collision. And the energy that's lost in the collision comes directly out of the energy that was the kinetic energy of the ball that was bouncing, right? And so any real ball bouncing any real floor will always lose some amount. And what they do to approximate that is they have a thing called a coefficient of restitution, right? Which is basically just a thing that says, let's have a number that tells us what percentage of the energy we retain after the bounce. So we just say, yeah, we're not going to simulate atoms like smashing into each other and losing energy and that and all whatever. We're just going to say, you know what? This thing loses half of its velocity when it bounces or something like that, right? Because we figured it out, and that's what it does, and the material science just says, okay, right? And all we have to do is just add in that coefficient of restitution, and then we will get a much more natural bounce happening, right? And you can kind of see those guys bouncing out kind of more the way that you would expect, like like we said, a fountain or something like that. I'm going to kick up the initial kick a little bit there, also just so we can have a higher sort of bounce to it. Okay, that may have been, I admit that may have been excessive. I'm gonna calm that down a little bit. So there you go, right? Now we're kind of throwing those guys out a little bit more. And I feel like maybe the bounce is even still a little bit much, even with a half. So I'm gonna take it down even a little further. So there's something that feels a little bit more like, a fountain of something spewing out like it is, right? And I'm reasonably happy with that. And as you can see, that's not a particularly onerous piece of code to write. That's pretty trivial. And we could even do this for some limited, like if we had a very limited collision geometry that we were working with, something very simple, we could probably do something with that. So it wouldn't be too complicated to have a couple things that happen, right, with these guys. And so that's kind of like the basic thing with like just starting to add a little bit of stuff into the particles there. Now, what I wanted to talk about in terms of what happens with the fountain here, there's actually some other things, and I don't really know, if we want to actually try this today. Maybe we should, maybe we shouldn't. Oh, it's such a hard decision. What do you go for and what do you not go for, right? I wanted to kind of talk about Lagrangian versus Eulerian simulation and just kind of how they differ and what they mean. And I don't know if we're going to be able to get through it in a day is the only thing. So I'm not sure if I should start talking about it, if I should save it for some other time when we're going to have a longer period to discuss it. But what the heck? If it comes up, it comes up. So let's just talk about it because it was on my mind. So what I kind of wanted to point out is so let's say we wanted this fountain to look a little bit more like a fountain. And one of the things that happens with a fountain of stuff, right, is that the upward velocity there is not so variable, right? The actual upward velocity in a fountain is in like or the spread, the horizontal spread, is much narrower, right? It's a much narrower thing that's happening there. And so really, for a fountain, we're talking about something that's really not going to have that kind of lateral spread to it. It's a very thin nozzle, right, like you can see, that's shooting straight up. And that's, what we've got there is a much more accurate depiction of a fountain on the way up, right? But if you take a look at what that looks like, and you think about what a fountain actually looks like, right? Well, our simulation right now looks like something that just kind of comes up here and then comes back down, right? So it kind of creates like a little narrow cylinder, right? But if you've ever seen a fountain has a very distinctive look. Any kind of a spray like that has a very distinctive look when it's got a reversal in its path. And what happens is it comes up, right? And this part is still roughly the same. But it actually then kind of comes out like this kind of a thing, right? So it's kind of has a narrow thing coming up here, and then it comes out like this, and forms kind of like a more of a mushroom on the way down. So the things coming down, right, are very different from the things that were going up, right? They don't. It kind of has this different character to it. And if you think about why that actually is, that is because these things are not infinitely compressible, typically what we're simulating, right? They cannot hold an arbitrary amount of themselves in a given area without a consequence. And what I mean by that is, imagine that you have a glass of water, right? The typical substance we might make to think about how a fountain looks would be, say, water, right? So if we have a glass of water, it's a fair bet to say that if the glass was filled up to here, right? Let's say your glass is half empty, right? Versus your glass is full. However you want to picture it. What we know about water, even from our daily, observations of it, you can understand this very directly because you've seen it all the time. The amount of water that is in a glass is directly reflected by how much volume it takes up, right? You do not have to ask how squished down the water was in your glass to figure out how much water you have. You know that you have exactly as much as the volume that you have. There is no density to water other than the one density that water has, right? And that is because it is an incompressible fluid, right? You cannot just squish it into an area like you might be able to do with a solid that had air in it that could compact down and become more dense and stay that way. Water will not do that, right? Water wants to expand to its natural density. It is an incompressible fluid in that sense, right? And so what happens with our fountain is, on the way up when we start shooting the fountain, everything is kosher because the water has an upward velocity that allows it to get out of its way at roughly the same rate as new water is coming in. So the water on the way up is pretty happy. But as gravity takes its toll, the water on the top is going slower and slower and slower until it stops, right? Eventually that first water that got shot out is going to slow, and at the apex of the fountain, at the part where it's going to change direction, it's basically motionless, right? And so what happens is you've just got this huge amount of water that's flooding into this zone right here that's going to try and come back down. But when it starts to try to come back down, there's more water there. There's water that was on its way up that is trying to occupy the same volume. And so what's going to happen is, as the water kind of comes up in and tries to, negotiate with its other water molecules for how are we going to occupy this space and maintain like a uniform density, it starts to push, right? It starts to have an outward force that is pushing water out of the way. New water that's coming in wants to push other water out of the way. Water that's falling down wants to push other water out of the way, right? So all of those interactions of the molecules is causing an expansion of the water volume at that point, because you're shoving new water into it, and the old water's got nowhere to go. It's got to leave, right? It can't just stay there. And to be clear, it's not like new water and old water are pushing each other outwards. It's more like there's just a collection of water, and as we put more of the water molecules in, it doesn't matter whether the new ones or the old ones or whatever are getting pushed out. Some water molecules are going to get pushed out because we can only have so many in a certain space, right? And so, if we were doing that in zero gravity somehow, you'd expect the expansion to be uniform, but obviously the whole reason this is even happening is because we have gravity, which is slowing the water down. And so what happens is you don't see much in the way of water shooting out these directions, because any water that got pushed upward is still under the force of gravity and will very soon find its own path downward that does not involve hitting any other water, right? And so what you end up with is that very characteristic fountain shape of water that comes up and then kind of gets splatted outward, in that way, because outward trajectories will never get pushed anymore. They'll just kind of be able to naturally fall, right? And so if you think about our problem that we have, if we were wanted to capture this, well, we could write some kind of special purpose code to do this, right? We could, if we just wanted a fountain and we just only wanted to simulate that, you could imagine having some kind of a force that kicks in. We just say that there's like a dispersal thing up here, right, that pushes it out. And that would be one way that we could fake the fountain thing, right? So let's write that fake one right now before I tell you a little bit more about sort of Lagrangian Euler stuff, so that you could kind of see where I'm going with it. So let's just write that one because it kind of turned into a little bit of a talky stream. All right, so if we wanted to write that one, what would we do? Well, let's just say that we have, at that apex there, we've got some kind of a thing that's going to push our water molecules out, right? So we're going to have a thing that's going to push them out. So what I want to do is say something like, and again, like I'm saying, I'm just writing a super cheesy thing here, doing the thing that is the effects artist's way of getting this done. Meaning we're not trying to do physical simulation, really, we're just trying to make something that looks like a fountain. So what I'm going to say is, if the velocity of the particle has gone negative, so it's went up and then now it's on its way back down, I want to make something that just makes those guys kind of poof outward, right? I just want them to poof outward a little bit, right? That's all we're going to do. So all I'm going to do there is, if they're on a downward trajectory, I'm going to, and maybe, we'll also check to see, they are within some reasonable bounds. So, and y is greater than some magical constant that we come up with, right? And these are going to be to kind of locate where the dispersal thing is going to happen, right? What we're going to do is we're going to say that whatever their x velocity was, right, we are going to maybe magnify it. Or you know what? We'll add a little bit of acceleration to their acceleration based on what the... we'll add a little bit to their acceleration based on whatever the their sort of displacement was in x. Meaning however far they were from the center line, we'll add a little bit of that back in, right? At least that's the, there we go. I'm kind of wanting to be able to type this in physics notation, which doesn't really work. All right, so let's try that and see if we can get something a little more sensible there. Right, I actually want to make sure that I do this in a strictly, it's a vector equation, so I got to make that keep happening there, but all right. So let's see. I've got a bunch of stuff that I'm going to have to tune now. I don't really know what these values are actually going to be. So let's see. That one we know. So this one's really the only one we have to figure out. I'm not really sure which one it should be. And I also don't really know how much the magnitude of this force should be. So it's really just, again, just kind of super tweaking these things to see what they might want to be. So it looks like... for some reason that's having more of an effect down at the bottom, which I don't super understand why that is. I guess probably because by the time it gets down there or something like that. Let me see if I can restrict that effect to a little bit higher and then maybe make it a little bit bigger. I wish I knew how high those things were actually going, of course, is the thing, but I don't. All right, so I'm going to make that force huge. There we go. And so I feel like my py here is wrong. I feel like it should only be operating at the top, but it's clearly operating at the bottom. So what did I mess up about that? Assuming that the velocity is negative and py is greater than 1. So its height above the ground should be greater than 1, right? Is it that just needs to be much higher or something? I guess. It does look like that was the case, right? So I don't know. Are we now at the point where it can't be added at all? It does appear that way. Yeah. So not particularly good, although I could also make it so we're just hacking the velocity directly. Again, this is all just randomly stupid hack sorts of things. I'm doing literally nothing smart here. Let's try it that way. So maybe 10x that? I don't know why. I feel like I should be seeing more. Maybe I'm not thinking about this quite correctly. But that is often the case with hacks. When you're just trying to figure something out, it's often not particularly smart what you're doing. So it can be kind of, yeah, there we go. So now we're getting a little bit more of that, but it's not really what I want. So I actually maybe want to make it so it's more like this, right? So it happens on the way up a little bit more there. Let's see. You know what? I could make it sort of only when the apex happens. So you know what? I could do it more like this. I could just do it in a bounds of y. So the bounds of velocity. So basically we do something like, you know, if it's in between that narrow band, so it's relatively slow, you know what I'm saying? Then we will do, you know, this sort of displacement based on its x position or whatever we want to do. Just so in that very narrow band, right? And I don't know if that maybe would make it a little bit better. Yeah. So of course at the bottom that's a problem. Oh, right, because at the bottom it will also have that velocity. Man, hacks are hard. This is why it's difficult to hack things, and I often try to just do them the right way. Because man, trying to come up with little things like this that do the sorts of stuff that you want is not always easy. It ends up being like, you know, this kind of war of attrition where you're like, oh, and then maybe I could hack this other thing on top of it. So it tends to be a little bit nicer to just do the right thing. So that's looking a little bit more, looking a little bit better, but only a little bit, right? Like it's still not quite there yet, right? But it's getting a little better, right? It's getting a little better. So let's see, maybe a little more. So if it's in between these two, so if it's relatively low velocity, so if it's less than 3 up, I'm going to make it so that it maybe we'll let it do a little bit more there. Right? So that's looking a little bit better. And you can sort of start to see that a little bit. I think another one of the problems is that it's just hard to take the sort of that narrow band and spread it out enough. So you almost need to add some entropy into them at the top there in order to get it to happen. But you know how it is. All right, so if I were to then say narrow this down even a little bit more. So let's say that the upward velocity is hardly jittered in any real way. So the upward velocity is like very straightforward, right? And then we've kind of got, you know, maybe even a narrower stream. So it's a very stable stream kind of going upwards, right? And then we go ahead and kind of jack that spreading effect up there, right? Let's see. That's actually starting to look a little bit better, right? But it's just kind of a little disquieting. I don't know if maybe if acceleration would be calmer or better as well. Yeah. I don't know. I'm not very happy with this. It's not doing it for me. I don't know if that's just because I want to do the right thing or if it's just because I'm not doing a particularly good job at hacking it today, right? The point being, either this is a good demonstration of why you should care about the thing I'm about to talk about next, or maybe if you're good at hacking stuff, maybe if you're better at like hacking stuff than I am, you won't have a problem, and you'll just come up with something that you know that's reasonable, right? So yeah. So let me tell you a little bit about what I was going to say in terms of how you actually want to solve these problems typically, if you can afford it. And sometimes you can't afford it, and then you're back to doing what I was just doing, where you're like, well, set aside a couple hours and figure out how you're gonna hack something to you know, make it work, right? So let's talk about this for a second. So why are we having the problem that we're having, right? With the original simulation, which was relatively physically correct. It's a bunch of particles that are being simulated by Newton's, you know, standard law of Newtonian motion, right? Newtonian dynamics. So why are we having this problem? Well, the reason we're having this problem is because all of the particles are just separate entities, right? They're not at all being considered. So what we actually would do, right, is when we have this upward stream of particles and we start having a collection of particles that are sort of occupying the space, and these ones are coming down and these are coming up, and we now have a high density of particles in the space, right? If we actually sat there and said, oh, for every particle, when we're going to simulate the particle, let's go collect all of the other particles that are in the nearby region, see how many there are, and if there are too many, we will consider that there to be a force that repels this particle away from these other ones, right? You can imagine this happening, right? So we could do that, right? But it would just be incredibly expensive because it means now we have these big queries to do for each individual particle, right? Well, it turns out that physical simulation on computers, like physics simulation, right? The actual, not the kind that we do in games where we're trying to approximate things for visual effects, but I mean like real physical simulation for like engineering and stuff. Actually considers two ways of simulating things, two like broad categories of simulating things because of this very problem. And they are called Eulerian methods and Lagrangian methods. And they're very separated in some sense. They're kind of very different. And what we are doing right now is what's called the Lagrangian method. And what distinguishes a Lagrangian method is when you have the information about what you are simulating is actually the thing that moves through the configuration space, right? So we are talking about a real, you know, our simulation space is like this X, Y, Z thing, right? And of course, we have this weird Y is up thing at the moment because that's how our renderer is built temporarily. So we have this sort of situation where we've got a three-dimensional space and we have some information about the thing we're simulating. And what we've chosen to do is encapsulate the information about the simulation space into these particles, and the particles themselves, which are the things that hold the information, and even more than just hold the information, they are the locations at which we do our simulation, right? We think about, I'm now simulating at this point, and I'm going to move it to this new point, right? Those simulation points are actually moving through the space. They are actually, the actual quantities of simulation are themselves evolving through the space, right? And there's another way that you could choose to think about this problem, right? Another way we could choose to think about this problem is in what's called an Eulerian, or as an Eulerian method, thinking about it in terms of things that are stationary. So instead of this, we could think of it differently. We could think of it as a discretized grid, right, in space, like so, where our fountain starts here, and it is producing particles of a velocity that are upwards, but instead of considering them as particles, what we instead consider them to be is just a density, right? There is just a density and a velocity at this location. So if I was to spawn 5 particles, let's say, and I was to, you know, their average upward velocity was going to be something like, you know, 2 meters per second, right? Then this cell of the grid would simply store 5 and 2, right? And 2 meters per second, right? 5 particles, 2 meters per second. And instead of ever even having particles at all, we would just have this storage of the grid, and the storage would be fixed. It would be however many it is, right? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, right? It would be a 6 by 5 array that stores that quantity per grid cell. And what we would do every frame is we would simulate each grid cell forward in time, but they would not move. Instead, what they would do is they would broadcast their quantities throughout the simulation. And there's a lot of different ways you can do this, obviously, and this is a whole branch of simulation. But basically what would happen is there would be equations that we would solve, or simulation steps we would take depending on how we wanted to write it, that would take the values in all the cells and try to determine what the next set of what the future time values of those cells would be for our next time step, right? So one thing we might say is, well, if there's a lot of particles, if the density is high and the velocity is upward here, then we should have, our equations should add particles to this cell, right? I mean, that's what would happen, right? And if that became true, then later this one would get more, right? And each cell would kind of add density, basically, to neighboring cells by virtue of the fact that it sees that the velocity should go forward, right? And there's many ways of solving this. Weirdly enough, there's Eulerian is... You might as well not even call stuff Eulerian, because Euler's got his name on so much stuff. I mean, for that matter, I guess so does Lagrange. That half the time you say the word, it doesn't even matter. It's like, which are the 20 Euler things we're talking about? But in the specific case of talking about physical simulation, if you said Eulerian method versus Lagrangian method, the person would probably know what you were talking about, right? They'd be like, oh, okay, I see. You're moving like particles through space, you're moving simulation through space, or you've got a fixed simulation grid and you're moving quantities through the grid, right? And so the reason I bring this up is because you can see how the Lagrangian method falls down at certain things which are about density, right? Lagrangian methods are very bad at handling density, because density is about how much stuff exists per unit volume, and the Lagrangian method doesn't even have a notion of volume. Volume has to be imposed on top of a Lagrangian method. So when you're going to go do a Lagrangian method that has to take account of volumetric forces, you're constantly at a disadvantage. Doesn't mean you can't do it, right? It just means you're at a disadvantage. And so Eulerian methods have the opposite problem. They have the opposite strengths and the opposite problems, basically. They're complementary schemes. What happens in an Eulerian method is things that have to do with volume are very, very easy, right? Because we've already said that everything exists in these nice little bounds. So if we want to talk about the fact that if things get too dense, they repel, well, that's really simple. We just go, what's the density in this area? If it's high, it needs to try and spread its density out. So basically it's like, look at two cells. If the density gradient, if this one is higher than this one, then it means it should flow this way. If the density here is higher than here, it means it should flow that way, right? It's really simple. And even without me even showing you how to do it, you can imagine in your head having a 2D array and going, even the totally crap hack version of that is like just looking at the cells, which one's greater or smaller, and just moving some density from one to the other, right? I mean, you can even imagine doing that. That's not exactly how you'd want to do it, but you can imagine it. Okay. So why do I bring this up? Well, I bring this up because if you add these two guys together and have them make a little love child flipper baby, right? You get, these kind of mixed methods, which can try to combine the two schemes, right? And so how would that work? How would we use that? And of course, we've got, 20 minutes left. So the answer of how it would work is, like I said, I probably will run out of time before I could actually implement one, because there's a bunch of stuff we'd have to do there and whatever. But point being, if you imagine how these things would combine together, you can start to see how we might be able to use both schemes simultaneously to produce an interesting effect, right? So let's suppose that instead of using the Eulerian method for everything, we use the Lagrangian method like we're using now, but we use the Eulerian method as an intermediate to try and get some of these volumetric effects happening, right? So, for example, if we were to do something like, I have a Lagrangian method, the Lagrangian method is shooting these particles up, right? And now I want to know if somewhere they are kind of bound, I want to sort of introduce like some forces based on where they bunch up. So when these things start bunching up, I can poot them out, right? I can make them start to disperse. Well, what I could do is say, okay, I've got the particle system as we have it now, but first, before I do the simulation on the particle system, or maybe after, depending on how I want to interleave the steps, I am going to take a grid, right? And I'm going to sum up the quantities I might be using in an Eulerian situation from the Lagrangian, right? So the Lagrangian frame is here, the Eulerian frame is here. The Lagrangian frame says, here's all my points. So what I'm going to do is just compute the density. So the density is like really high here, right? I'm just going to add, for every grid cell, I'm just going to add, I'm going to count the particles. Every particle that's there, I'm going to add it in, right? You know, so I've got like 20 here, and there's like 2 here, 2 here, 3 here, 2 here, 1 here, something like that, right? I'm going to do that. And then what I'm going to do is I'm going to do some kind of an update step on the grid to see which cells are high density. I could even decide if I was super cheeseball, I don't even have to do that. I could just do the sum. And then what I could do is say, well, when I go to do my simulation now, my Lagrangian step, which is going to update these guys and move these guys somewhere, right? Instead of just updating the particle in isolation using the techniques we just did, which are the kind of Lagrangian way, just simulate it forwards in time, moving the point through, I'm going to do an Eulerian style lookup and say, what's the stationary density at this point? And if that density is high, I will, introduce a velocity that moves things from high density to low density. So for example, maybe what I'll do is I'll take this cell and I'll subtract the density of this cell from it. And based on the gradient, I will add in a velocity this way, or acceleration this way. I'll do the same thing here. I'll do the same thing here to produce a final composite velocity or acceleration that I add in as like an Eulerian term to my Lagrangian update, right? And so that way I can sort of do something where I do allow my particles to be considered as density groups in a kind of relatively clean way that doesn't really hack it, right? It doesn't really force it to be about a fountain. We could do anything we want here where we have, particles spraying around, and where they happen to, where the spray happens to concentrate, they will, disperse from there or whatever, right? So you can kind of see how you can start to construct a more physically accurate particle system out of this without really having to do n-squared loops, because that's the real problem in the Lagrangian, right? The real problem in the Lagrangian is if I have to consider other particles when I could talk about one particle, that ends up in an O(n) squared land, right? We have n particles, and if each one of those n particles has to think about all the other n particles, that's n times n. And that's a very bad runtime for a particle loop because n is going to be high, right? If we want 4,000 particles, well, now we've got 4,000 times 4,000 things to consider, and that's no good. Instead, what we'd rather do is say we've got 4,000 particles, right? And we've got, some fixed number of 64 grid squares. So now we know that we're 4,000 times 64. And we don't, even if we drive this number up, this number gets no worse, right? We can have 8,000 particles, this number still gets no worse, right? Instead of the n squaredness, whereas we drive the particle count high, this becomes a disaster because it's 8,000 times 8,000 or whatever, right? So hopefully that makes some sense. What does that look like in practice? Like I said, it's completely unlikely that I'll be able to do anything remotely resembling a mixed method integration scheme here. Well, I shouldn't say integration scheme, a mixed method physical force simulation. But, what would it look like? Well, it would look like something like this, particle cell, right? And in the particle cell, we just have something like density for now, right? Density, and you know what? We probably have average velocity. Right, and maybe I guess we'd have velocity times density. Actually, would be what we'd have, right? Something like that. So as it comes in, we would get that sort of we could normalize the velocity out. So something like this, right? And what we would say is when we have our particle system, we would then have our particle cell, right? And our particle cell would be a two-dimensional array that again tries to capture this thing. So who knows what it is? It's 16 by 16, let's say. I'm not sure. And then we would go in and do exactly what I just said on the blackboard, which again I said it's just a lot of code. So can we do it in a day, in 15 minutes, let alone a day? Probably not. But it's something like that. So we have something where we'd do I don't know x is 0, x is less than 16, plus x. Right, u through y equals 0, y is less than 16, and this is really, define particle cell dim, something like that, so that we don't have to have a magic constant strewn everywhere. We can change it easily. Something like that. We do this, right? And maybe I'll do it this way. We do this and we say particle cells, right? Yx. We're gonna clear it out, right? We just want it to be zeroed first. Although I guess now I think about it, we wouldn't have to do that in a loop. We could just say 0, right? We could just 0 that, because they're all going to be at, we know that there's no special values that it has to be initialized to. So we could just say, you know what? Go ahead and 0 the whole thing, right? So we can do that. And then what we want to do here is we would want to be able to do that summation, like I said, right? So we want to figure out where all the particles are at the moment. And then we want to add that kind of force in instead, right? So we know it's all 0 now. So what we're going to do in here is we're going to run through the particles once, taking their locations and putting them in, right? So it's a little bit, again, you don't pay n squared, but you do pay like a second pass, for example, because you've got to compute that grid first. Now, what we could do, there's yet another way we could do it, which is you compute the grid on the previous pass. So we can actually get rid of this and have a 1-frame lag in the pass. There's all these other things we can do, but I don't want to get too complicated. I don't want to throw too much down just yet. So let's just do it in a separate pass first, right? So what I would do here is I just need to know which cell I'm in, right? I just need to know for the game state, for whatever the particle cells are, I just want to know which of these cells I'm actually going to land in. So I'm going to say particle cell equals, whatever this cell is. And we'll figure out how to compute that y and x in a second. So when I have that cell, what I'm going to do is I'm going to take, again, we've got the density there. So I'm going to take the density, and I'm going to add whatever our density is to it. And for now, we'll just say that the density of every particle is 1, but we could have particles that are like more or less dense. And then I'm going to say the velocity times density is just going to be equal to whatever our particle's velocity was going to be, right, times whatever our particle's density was, right? So we're basically summing up those two things. And what that means is that now, when we go to look at the cell, we know what the average velocity was weighted by density in that area, right? Because we can go ahead and divide. We can take the density and divide out the velocity times the density to find out what the average velocity was. Right? That makes sense. So yeah, so we can do something crazy like that. And this would give us a cell to sample from if only we knew the y and x, right? But that's pretty easy. We've done stuff like this a bunch of times before, right? You've seen us take things that were not on grids and stick them into grids, right? And so all we really need to know is where the base of the grid, like how to basically map our coordinate space onto the grid. So I'm just going to take an arbitrary thing and say, okay, the base of the grid is going to be at like, maybe -5, 0 or something, right? Because here's where our fountain sprays things out of, right? So maybe it's -5, 0 or something like that. And this is going to go out to, or I shouldn't say -5 because it was 16 or something, right? So it's -8, 0 or negative the span divided by 2, right? So it's out there somewhere. And then this is going to go to 8, 0. And then this up here would be, 8, 16. And this would be -8, 16, right? And so all we really have to do is take the position of the particle, right? And turn it into an integer and stick it into the grid. That'd be fine, right? Because again, we're not trying to do anything particularly fancy here. Nothing particularly weird, just something basic. So what I want to do is I want to do a round, so I can just kind of see, or actually I guess I want to do a truncate to put it into a cell is probably a little more reasonable. So we have those that we've done multiple times. We've got our truncate. So I'll just truncate it, right? We'll have the particle, well, this will actually be P, right? Particle.x and the particle.y. Now, each particle, its position, is pretty much the exact thing we want, only it's offset by a little bit. Because remember, our grid doesn't start at 0, 0 as far as the particles are concerned. It actually starts over here. So all we really need to do is just first compute what the P would be if we subtracted the origin of the grid, right? So we have the grid origin here. And that's a really easy thing for us to figure out, right? Because like I said, only the x is really different. Everything else is the same. So we've got whatever this particle cell dim here is. We just need to go ahead and say, okay, yeah, the particle cell dim, we're just going to do negative half of that. So that way it's kind of centered around x. So that's our grid origin. This will do all the summing, and the only thing that we really have to do now is make sure that we clamp these guys to something reasonable, right? So if x is less than 0, it equals 0, right? If x is greater than that particle cell dim, right, we need to truncate that down, like so, right? And the same thing would be true for y. So now we know we're always in, we're always in the cell. And we could also, after we do this, scale this guy. So if we wanted to scale the grid, we could do that too, which is, it's pretty easy. So again, if we were doing this for reals, we'd think more about how the grid has to get overlaid and all these other sorts of things. But for now, that seems pretty reasonable. And that should like get our grid going just fine, right? Of course, we can't, that's going to change the data layout, so I got to rerun the program, right? And so now we're actually computing those grid values, and that's all fine. We probably need to draw them a little bit in order to kind of see what's going on. But you know what? That even that is not particularly difficult, right? We could pretty easily just do a push rect here, where we actually draw out what our grid looks like, right? And so what I could do is say, okay, I'm going to do a quick spin just for our own like edification, right? So we can see it. I'm going to do a quick spin over this grid, right? Over the grid, just so we can kind of see, what we're even computing here. So I'll do that. I'll go ahead and say that we'll spin over the grid, right? Yeah, and as we do that, I'm going to go ahead and pull out that particle cell. And then I'm going to draw a rectangle that's going to be centered, or I guess is going to show us the grid location, and is going to maybe be colored based on the density, let's say, of what's there. Again, I've got about 10 minutes left on the clock, so I'll just, or I don't even remember, I think it's something like 10 minutes, 7, 8 minutes, something like that. So we'll go till about 6:08. So if I wanted to do that, right, I know that it's, again, just x and y, nothing particularly fancy there, but it's offset by that grid origin, right? And so whatever the grid origin is, we need to add that in, okay? And the other thing that we need to do is recognize that this dimension thing here, we know that we're drawing something that's like that, but the problem is I believe this was centered the way that we draw our rects, right? We really need to like lock down the render sometime soon and document it so that we know how our stuff works, so we don't have to keep looking. At some point, that's a good idea to do, let's say. So anyway, but if we push rect here, I just want to see which one we do. So there's the offset and the dim. So it looks like scale times dim. So it's actually going to be up in the actual code, it looks like, where it does that displacement. So there's rectangle. Entry P plus dim. So no, it's actually corner. It's actually corner and width height. So that should actually be it, right? That should actually be the thing. What is this complaining about? Oh, just these guys. Do we have that already? No, we don't. All right, so if I go ahead and make this happen, there we go. No user-defined conversion from, what are you talking about? Oh, this is just a V2 is the problem. There we go. All right, and so what I can also do here is I can make the density proportional to, I can make an alpha value here, right? Which is going to be like clamp 0 to 1, whatever the density of this thing is, and maybe we say that it's like, it's a tenth of the particle count or something like that, right? So we're just going to want to just kind of get brighter based on how many particles are in that cell or something, just so we can see if this is working at all, right? So let's go ahead and, okay, that grid is way too big, first of all. I guess that makes sense because each grid cell is a meter. So let's start by calming that down a bit. So let's introduce a grid scale, right? And the grid scale should maybe be, 0.2 or something a little bit more coherent there, right? And so what I want to do now is I want to say that we got the grid scale times that, just to kind of shrink things down properly. And so that does mean also that these values have to be multiplied by the grid scale as well, right, when we're drawing it. And similarly, this would also be multiplied by the grid scale, right? Because we're sort of shrinking everything down a little bit, right? Okay. That is not right, and the reason is because this, of course, also needs to be scaled by the grid scale, if that makes sense, because it's going to be too far away, right? Now it's being moved as if there was no grid scale, so the actual origin has to be computed knowing that that's how far it's actually going to go per step as well, right? All right. So there we go. So that's looking roughly right, but we're not getting the right density calculation there at all, as far as I can tell. So let's figure out what's happening there. Why is that not working properly? Density density plus equals cell. That why is that bad? It looks reasonable, and yet it is apparently not reasonable. Yeah, I don't know. I'm gonna do this instead, just to make sure that I don't have any weird things happening with alpha. Yeah, that's just totally wrong. Well, that's okay. Let's step in. Got a few minutes left. You never know. This could still work. You never know. If you can get something in before the end of the stream, it's always kind of tricky. All right, so let's scoot on back here to, where is that particle fun? It is right here. All right, so let's come in here and let's see what we tend to get for x and y values. Okay, well, that's not helpful. What is going on there? Oh, pfft. Okay. Yeah, wow. So obviously the idea here, right, is to scale, we want to map things into the space of the grid. So what I did here was I actually made the problem worse, right? I multiplied by the grid scale, which will shrink the values. I want to make the values larger so that they move into more grid, right, spaces, right? If our grid, if here's our x, here's our origin, right? Here's 0, 0. And I've got a particle, right? And it's, it's going to the value like 0.7, 0.3 or something, right? If I want the grid to be smaller, so the grid is like 0.2 on a side or something, if I want to know what grid square this falls into, the last thing I want to do is make this value smaller. This value needs to be bigger because it needs to fall into 3, right? So I'm really supposed to be using 1 over the grid square, right? I'm trying to figure out where it actually maps. We've done this before on the stream multiple times. It's totally spaced, right? So I actually need to know the inverse of the grid scale so that I can map it that properly. And that's actually what I actually wanted there, right? So that was just being stupid. So let's try that one more time. Okay. So now you can see a little bit better what's going on. Of course, our heads are offset, which doesn't help. So we should probably use something that's actually centered. But it's kind of cool, right? You can kind of see that now we kind of know what the density is everywhere. And if I go ahead and make it draw after the fact, we can see it a little more clearly. Oops. Right? So there you go. And so you can kind of see where the densities are. You can kind of see where they are sort of adding up. And so if we wanted to now, we could sort of have things that make them disperse based on those densities. Yeah. So it's a little bit confusing to watch because as you're seeing it, you're seeing kind of not the true answer because this is what the densities are without the fact that when they get to the top, they would start to disperse. So this part is going to be brighter than it should be because everything falls straight back down onto it, right? Which is not actually correct. But yeah, there you go. So that is the start of a scheme, but we don't really have time to do anything any more fancy with that, right? Because of the lateness of the hour, shall we say. But what we would do is we would do the exact same thing in here, right? We would pull this code out into something common, right? But then we would do, exactly the same thing here, where we grab out whatever the cell is for this guy, and now we can use the cell's information to do whatever we want to do, right? And so, for example, even if we just were to take this thing here, we could, instead of doing this as an if statement, like we were doing it before, now we could actually just add something proportional. If we wanted to do this thing proportional, we'd just add in the term here for whatever the density was in that cell. So the poofing factor could now just be based on the cell density, right? And off you go. And hey, that actually does roughly what we actually wanted it to do. Of course, we're adding a little bit too much force there, to say the least. But at least now we do have something that's kind of dispersing those guys a little bit better. So we have one other thing that we need to do, which is that we don't actually cap our, particles that have gone to nothing don't actually are still accounting for everything. So what we might want to do too, just temporarily, is say that the particles alpha, since that's our kind of lifetime factor, is what the density actually would be there, right? So now you don't have those ones that are kind of fading out, don't actually count for any kind of for any kind of a density factor, right? So yeah. So if we wanted to play around with that a bit, now we could actually try playing around with some forces there. Of course, it's a little bit confusing because since we haven't done work on the grid, which is the important step of the Eulerian part, we don't know what direction to shoot particles. We don't know how to move particles in any particular way. So it's kind of bogus, and this is never going to produce anything particularly interesting. But point being, you can see that we're kind of getting a start to it, where we can sort of start to get it where things are kind of moving away from where they should move away from. But of course, we also have things where you can see them kind of bouncing off the things there, and part of that is just what happens when you get to the edge of the grid. Now, I could expand the grid out a little bit just to sort of prolong the bad, or keep the badness a little bit less problematic. But again, because we're not solving what the density says you should do, because we need to look at neighboring cells, it's just going to keep accelerating guys, right? Anywhere there's density, it'll accelerate away from zero, which is just not particularly useful, right? It's not a particularly useful force. So we're still not quite to the point where we don't have to hack it. I mean, we could hack a little bit more of it, which is just to say, if the cell density, has to be higher than a particular value or something like this too, before that happens or something like this. And that would calm things down a little bit, but it's still not going to be, it's not going to be good enough, right? It's not going to be good enough. It's still not going to give us the effect that we want. But it's starting to get there. In fact, you can already kind of see, even just from this, you can kind of see how it's already starting to disperse at the top more, right, where that density starts to build up. But again, there's a bunch of stuff we would need to do in order to make this more correct, and they are operations on the grid. First of all, that would look to see, because first of all, you would look at the velocities, and the velocities, if things were already going to move out of the cell, right, you would not feel the need to disperse them if they were already moving into a place where there would be room for them, right? And secondly, for density, you would only move things from places of higher density to lower density, whereas right now we're not looking at that at all, right? So yeah, so again, totally bogus, but what are you going to do? I suppose the thing we could do, even just quickly, now that I think about it, that wouldn't actually be too hard to do, is we could do the sort of next door neighbors sort of a look up in the grid, which is where we do something where we keep these guys a little bit more truncated. So we say something like you gotta be inside the grid by 1 square. So there's always an apron, right, or whatever. And then what we'll do is we'll actually check the neighbors, right? So what we do is when we look up the cell, right, we've got a couple here cells here. We've got a cell, you know, that's to the left, right, 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 something like this, and we would just basically have all the different cells. So we'd have y plus 1, which is the up one. We'd have y minus 1. We'd have y plus 1, which is right cell, and then we'd have our center cell, right? And then we would literally just go through, and instead of any of this nonsense here, right, we would do something like, you know, like dispersion. We would initialize it to 0, and then we would say something like, okay, the cell center density, going from the left cell, going from our cell to the left cell, what's the density gradient, right? And we're going to add to the dispersion some quantity, you know, some proportion of that, right? Which is, you know, whatever our coefficient of dispersion or whatever is here. Whatever the density difference is, we'll add a force in that direction, right? So if the density in the left cell, I guess I should really do it the other way around. If the density coming from the left cell to us, right, if we are higher, then what we want to do is add a force that pushes us towards that cell, right? And we would literally just do this for each of those differences, right? Or maybe down up would be the correct order there to keep parity, but right? Does this make some sense? I'm literally just checking the neighbors to see what the density gradient is between the two, and then I'm just adding a force that moves things from a direction of low density to one of high density. And I don't know what that's going to do. Again, it's like, don't really, you know, this is very ad hoc. So all I need to do now is just kind of move that coefficient up a bit and see, you know, if that yields anything beneficial for us or if it's just kind of a waste of time. So I'll crank it up a bit, and we'll see. All right, that's not very... Oh! It would help if I ever added the dispersion into anything. Awesome. Yeah. Let's try that again. So yeah, our particle acceleration... That's pretty funny. So our acceleration is going to be whatever the constant acceleration is for the thing, plus our dispersion, right? Man, that was stupid. All right, you know, sometimes we're stupid. Sometimes I'm very stupid. I've been known to be extremely stupid. So there you go. Now we've got our dispersion going on, and it moves things between our cells based on that density, right? And so you can see that that actually works it's very well behaved now and does sort of what we want. But it's still not quite the right fountain shape, and the reason that it's not quite the right fountain shape is because we don't account for that velocity movement of the fluid, right? We don't account for the fact that if the velocity was already upward, so these particles were already going to vacate the cell that they were in, we don't have to move them out of the way because they're going to a new location already. So we need to kind of think a little bit more about that. But you can already see it starting to take shape slowly, right? And so we're getting somewhere, is all I'm saying. We're getting somewhere. All right, so I hope you enjoyed that brief introduction to physical simulation, Eulerian, and Lagrangian methods. It's a bit of a butcher job because we had to do it in one day, but what are you going to do? It was kind of interesting. I had fun with it, to be honest. It was kind of fun to just suddenly do a composite Eulerian Lagrangian simulation of a fountain today. But it's overdue for the Q&A. It is overdue. So let's go ahead and go. Now, I threw out a ton of stuff at you, so hopefully you got some questions because I covered it very sparsely. So I hope that you will ask some questions so I can go ahead and clarify that. Now, we got a good 15 minutes left here. And as Z said, I suppose adding some friction to dpx might help. I agree with that, especially on that bounce. In fact, if you wanted to add that friction, it'd be pretty easy. We're not really simulating the kind of contact area very well or anything like that, but on the bounce, we certainly could do it. You could say that the coefficient of restitution was actually going to be on the entire velocity, right? And so instead of doing it this way, we could do something more like this, well, actually, typically you've got two, right? There's actually usually two of those, right? So, you know, maybe the coefficient of friction is something different or something lower, right? But you'd do it, I guess, like this. Yeah. And that would be some friction to just slow that lateral motion down, right? Oh, whoops. I didn't mean negative. There we go. So that would be something that kind of deadens that lateral, you know, that lateral thing there on impact. But there's reasons why that's, oh, I should make that much weaker. There's reasons why that's not exactly the best thing, but for particle system, it's probably fine, right? If that makes sense. Try reducing the size of the individual cells. So you want to just make more cells or something? Is that what you mean? Like you just want to see what happens if we have a higher resolution data. I mean, one of the things that we haven't done, like this is very ad hoc, right? And so one of the problems is we haven't the volume. I'll run this and then I'll say what I was going to say. Right. So, oh wait, I got to change that grid scale down a bit. Where is my grid scale? Where my grid scale? There it is. So I'll say something about that in a second here. Right. So there you go. That's with a denser grid. So let me say one thing about that briefly though. So if you were actually doing this, like if we actually sat down and we're like, okay, we're going to make a full-on Lagrangian or Eulerian particle system for Handmade Hero that's going to be like a real thing that we use a lot and we care about it, right? There's a problem with the way I did this ad hoc stuff, is you can't just add a force that's like, what's the difference between these two cells? Okay, there's the difference, add the force. The reason is because you haven't taken into account the volume of the cell. Because the volume of the cell and the distance like between cells, right, would change how big that force should be. If you don't want to look at the delta between two cells this way and then a delta between two cells that are this size and add the same amount of force for the density gradient, right? Because it would take more force to move things from this area to this area than it would to move them from this area to this area. So you need terms in there that account for the size of the cell, right? So I guess the way I would say is right now the way we've written it, it would have to be tuned for a particular cell size. Whereas you could write it in a way that, although it wouldn't be completely oblivious to the cell size, because the resolution of the cells has real effects on the simulation, obviously, it would at least not require the constants to be retuned when you changed it. Back of the head would make a better particle than side of the head. That's probably true. If you want something even freakier, we could do something way freakier than this, actually, though. And that would be, instead of doing first asset from, we do get random bitmap from. And then we would need to pass the, let's see, handmade asset get random, oops, random bitmap from, where is it? Get random bitmap from. So it'd be assets, type ID, series. Game state, effects, entropy. Did that? Why did not? Oh, oops. That was a mistake. Okay. So if I go down here, and where we are actually asking to, you know, get, where we were actually asking to get the bitmap, what I could do is say, get random bitmap from game state effects entropy. And that way we just have random heads, and they'd be flickering all around and crazy, right? So yeah, if you want some like crazy shit, that's that. Ooh, man, third swear. If you want some crazy stuff, that's what it would be. And you can also add variety to the particles too. Like if you wanted to, right? You could do something where this bitmap ID, so the bitmap ID would actually be on the particle, right? And if you did it that way, then what you do is when you actually spawn the particle, the thing would get picked at that time. So the bitmap ID for the particle would get picked when it actually, you know, when it happened, and then the bitmap ID would be something that was stored with the particle. Again, this is all about, again, making trade-offs of like, how complex do you want the particle system to be? How expensive is it versus how versatile are any individual things? And so then you got kind of the various like, particle, all the different heads in there. And pseudonym 73, I see that you said, if you're going to alter the grid scale, you probably need to scale DC by it too. I'm assuming you typed that before I said the explanation of that. Yes, like I believe you work in this kind of a field in general, so you know probably better than I do exactly that thing, which is that, yeah, like if you actually want to do this right, you have to work out the forces based on the actual meaning of the grid cells, and so the dimension of the grid cell is a critical component of the scale so that you don't have to like change things like DC, right? Did you ever add a way to tell the music to shut off, or did you just disable it? I just disabled it. What happens if the particles respond between two cells? Will that cause an effect where everything will just not bounce off each other anymore? I'm not sure what that means. There's really no way to put a particle in between two cells. It's going to fall into one cell or the other because... yeah, so I'm not sure what that means, sorry. On API design, you recently emphasized write the usage code first and then the implementation later. While compression-oriented programming is about writing code first and then compressing it, pulling code into functions where necessary, allowing the API to evolve out of that process. They seem like two contradictory methods, are they? How do you decide when you're using one or the other? So no, I don't actually think of them as contradictory at all, actually. Which is weird, I know. What they actually are is, if I sit down at the computer and my goal is to reduce the amount of duplication in the code that I have, so I'm looking at a thing and I'm like, I have to reduce the duplication of this thing, right? Then I already have all the information that I need to do that job. Compression-oriented programming just tells me, here's what I need to do, right? So the always write the usage code first thing, the way that it would be contradictory would be if you said you should do that then. Meaning I sit down and I have all of the working stuff that I need, like my code is doing what I wanted to do. And then I sat down and wrote, the usage code for it first or something like this, right? And I said, well, okay, I'm just going to go write a bunch of usage code and then try to reverse map that onto the thing. That's not usually how I think about it. The way that I think about it is, if I don't have anything yet, meaning I don't know what it is that I'm supposed to be writing, I have no idea, right? Or I could make up ideas, but I haven't yet, right? That's when write the usage code first is the thing to do. So in other words, what we did on the file API thing, it wasn't like I had a bunch of code working that was loading in the assets in the streaming way or whatever, right, already. And I was just saying, okay, what I need to do is make this reusable. We just didn't have an API. We didn't have any code that was doing it, right? And so when I say always write the usage code first, what I mean is, okay, so now what I need to do is I need a thing that does this, whatever it is, and I don't have one. So rather than going and starting to formalize something, like go and writing an API without having any idea what the thing, who's going to be calling it, I prefer to do the opposite, which is to like go write the usage code that is the thing that I wanted to have, and then I'll go implement it, right? So I really see them as not actually being contradictory, because they're actually not doing the same thing. It's not like you could get, I don't think of it as being possible to get to a point in the program where you could do either one. You can only either do one or the other, and it's based on what you have in front of you, right? And so if you don't have anything, you write the usage code first. If you do have stuff, then you do the compression-oriented programming. And another way, there's top-down versus bottom-up programming is another way to think about that, right? Like that, those are phrases that are used a lot in the older school literature, right? Where it's like you have to go the direction from stuff that you have to stuff that you don't have. And if the stuff that you have is at the bottom, you need to go upward. If the stuff that you have is at the top, you need to go downward. And so compression-oriented programming is saying you have a bunch of bottom stuff you're trying to fix. That's compression. Do compression. Look at it, go, how do we pull out pieces that do the same stuff here, right? If instead what you have is an idea of how things are supposed to happen, but you don't have anything to make them happen, then you need to go downward. And that's like when I say write the usage code first, right? So I don't know if that, maybe that didn't explain it very well, but that's the way I usually tend to think about it. It's like there's an empty spot, a void of information. And if that void of information is more specific than the code you have right now, then you are writing the usage code first. If that void of information is less specific than the code you have right now, you're compression-oriented programming, right? We need another. There was Snuffleupagus, but then I don't know what the other way what the other direction would be. Would it be possible to split the fluid computation across two frames, like use the first frame to accumulate velocity and momentum changes and the second one to resolve them? Yes. And I think I mentioned that when I said it before. I was like, we could, I'm going to split this into two passes, but we don't have to. We can make that a little bit, we can make that not do that by using two of the cells, right? One from the last frame they're going to sample from and one from the new frame. But sometimes that actually is a lose because now you have more memory, and so your cache performance can be worse, right? So you don't typically want to do that stuff unless you really know that's a good idea. Does the size of the grid relative to each particle matter much? Yes, it does, and that's one of the problems with these kinds of systems, to be sure, is all computational physics stuff is kind of ad hoc in that way, where it's like, yep, it's like we're just making approximations that, and so it definitely it is sensitive to it. If the cells are too large, the simulation won't be accurate enough, and you won't be able to capture some of the phenomena you need. If the cells are too small, then you will never accumulate enough particles into them to actually have them do anything, right? Say you're deciding whether to bounce the particles off based on the density now, then if the particles respond between two cells, wouldn't the density be halved and not bounce off anymore? Oh, I see what you're saying. You're just saying if the width of the particle stream is wider or is moved. And the answer is yeah. These schemes are not awesome, right? There are things you can do to help mitigate that. For example, you can give particles actual area and add add to all four. So the way that you can solve that, or not solve it, but mitigate it, is to do the bilinear thing again. So if a particle is here, you add its density to these four centers based on its proximity to each of them, right? And that gets you out of the business of the in-between two cell spawning problem that you're talking about, where you've got some particles in here and some particles in here, and now you're trying to talk about the density there, right? So there are some things you can do to help mitigate that. But again, all methods that involve discretizing things to a grid have a lot of problems like that. And so you just have to be okay with knowing that the goal here is to produce some kind of effect. And if you can produce it with a discretization, it's okay. But is it going to be perfect? No, it's going to be very far from perfect. Let's see. Would simulated annealing work for this issue? What issue? I'm not sure what the issue was. Doesn't writing usage code first imply simplicity in API calls? Well, yeah. That's one of the metrics that you would be trying for. Doesn't this box you in when trying to create persistent things on the stack? I don't see why those are even related. All complex initializations for persistent objects have to be done somewhere. That is true. If done on the stack, how do you persist complex data structs without using static? Well, if you're persisting it, you wouldn't put it on the stack. If by the stack you mean the program stack, you would put it on its appropriate lifetime stack, right? Like we've been doing in Handmade Hero. So I'm not sure I understand those questions, really. Brain Cruiser, current simulation is in pixel space. No, it's in meters. Are pre-rendered effects viable? Well, in Handmade Hero, they probably aren't something I would want to do, because this is about programming, and so we want to do things that are programmery. And so I would say most of the time what we want to do is do our effects dynamically, right? Because it's just more learning that way. Like, we learned a bunch of stuff today, even just hacking around with this, and like, are you ready to go off and write your own physical simulation code? No, because we only just kind of brushed against it in a very, very quick and dirty way. But, you can see that doing effects like this, when we say let's figure out how to program them rather than having an artist make them or something and then just play them back, you learn a lot of programming that way. So I think that's pretty important, and it's kind of what I would like to stick to on the stream as much as possible, right? So there's our lovely fountain. It's kind of cool, actually, I feel like. I'm liking it. I feel like our D alpha is maybe a little high, though. I feel like our D alpha maybe wants to be smaller, so we can kind of see it. It's just kind of fun to see it pile up a little more, right? Do you see how it's doing some pretty cool stuff there? Like the water isn't getting near the nozzle because the nozzle is very high density down here, right? It's just kind of fun. Like even already, like that's what's cool about leveling up your physics simulations a little bit. Not that we've really done much of a physical simulation here. We've done the simplest, dumbest possible thing, right? But that's already so much cooler than the hack we were doing, because now it's actually starting to capture some of the phenomenon that you might want, which is the water staying away from other water, right? And dispersing itself out in that way. And so, you know, it's just cool. All right, so we're over time. We're about 8 minutes over time, so I'm gonna call it. I'm going to call it a day. That's kind of cool. That is just fun. I mean, you know, you got to admit that a spewing head, a fountain that sprays heads into the air is pretty cool at some level. I wonder what would happen. This is always what you get if I decrease the spawn rate a little bit too. I'm interested to know what would happen there. Looks roughly the same, but you kind of get a little more. It's like less force on the nozzle, so it gets a little more. It's kind of throws them up a little bit more as they kind of get into spurts that will. Yeah, God, it's physics stuff is just cool. It's just cool. And so there, you know, if I spray it out more at a time, again, haven't given them any more upward velocity. I've just increased basically the hose, the pressure on the hose. It's just fun, right? I mean, that's just fun. There's nothing better than the crazy physics stuff like that. It's just amusing, right? That's great. So I think, you know what else it would be nice to do at some point too. I mean, we're not really supposed to be working on particle systems right now, so maybe we'll revisit this in a while. But we'll also want to do things so that, you know, they could kind of be more stationary. It's kind of fun. I wonder if we should just do like, oh, next week is particle systems week. Probably not. Probably not. We do those later. All right. Okay, I'm gonna close everything down. Particle systems. Who doesn't love particle systems? All right. So here we go. Thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. I hope you enjoyed our brief foray into particle systems and that it's gotten your interest piqued in such things, which we will maybe talk a little bit more on later on in the project when we want to focus on effects for a bit. But until then, if you would like to play around with the particle source code or anything other source code, if you pre-order the game on handmadehero.org, it does come with the source code, so you can check that out and download it every night after I'm done. I upload new zip files so you can always have the latest. Also, we have a forum site if you'd like to come ask questions, or if you want to download ports to Mac and Linux that community members have done, they post them there. There's also an annotated episode guide maintained by the community that's pretty cool. We have a Patreon page you can subscribe to if you want to support the video series, and we have a tweet bot, which tweets the schedule at you. So if you want to catch the series live, you can do that. And speaking of catching it live, we will probably be back here Monday, 5 p.m. Pacific Daylight Time next week. But just to be sure, do check that tweet bot, because sometimes we have to do other schedule things depending on my schedule for the week, just to make sure we can all fit it in. So that's about it. I hope you will have a particle-filled weekend and have fun coding. I will see you on Monday. Take it easy, everyone.